granular flow, the basics of granular flow. I'm going to say as a precursor, I've never really done any modeling. Not really. I never have ever done any modeling of granular flow type problems. Most people, there's really nobody at ITASCA that's done much work with granular flow problems other than like stuff coming out of ore passes. And so this is going to be kind of just a basic overview of that kind of an area. And let's jump in. So look at this. This is a journal paper. It's got this great title. I love this. You guys all know about the Beatles song, All You Need Is Love. Da 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 da. All you need is love. That's one of their famous songs. So this professor actually had the gall, sort of, or whether you like it or not, he's a kind of a showy professor. He likes to do things that make people remember. So he wrote this journal paper, All You Need Is Shape. Okay. And what he does here is he uses a 3D discrete element program, but he's not a distinct element program. It's a different program. It's called LSDEM. And what this program does is it has this really cool way of representing any kind of shape. So he doesn't have to turn it into a polyhedron. Okay. And what he's able to show in this thing is he takes the actual shapes of a bunch of sand in all their complexity, and he makes a whole bunch of particles with those shapes, and then he essentially just puts in the linear contact model. And he basically gets this incredibly good response of this dry sand when he subjects it to different triaxial tests and things. And so what this is saying, what he's arguing, is that really to get your granular systems right, the most important thing is shape. And the contact model is kind of a second order thing. And so even with a linear contact model, he's getting really great results, right? We could do the same thing in PFC, but we can't quite do the shapes as well. We would have to turn those into polyhedra, rigid blocks. But we're also has been found that we get really good behavior with those things too when we account for the shape. Now, when people are doing industrial scale mixing and granular flow systems, they find that if they just use spheres with any contact model, doesn't matter. If you just use spheres, well, hold on, forget what I said about contact model. If they just use spheres with linear contact model, they get very poor response because it behaves like spheres in a big flowing out of something. But most granular material is not spherical. It has different shapes, like rice, for example, right? Or pieces of coal or something like that. But they don't use rigid blocks or the equivalent in other codes, polyhedra, because they're much too slow. You know, they want to do millions of particles to do these things. So they have developed this special contact model that makes spheres dance as though they are not sphere shaped. And here's the idea of the contact model. First of all, it's called rolling resistance contact model. So let's talk about the physical system here. So there's a collection of spheres, and let's say it's a big giant packing of those, and we're going to look at one, and we're going to force it to rotate, okay? The only thing that resists rotation is shear force that builds up on the edge of that sphere at these contacts, right? And that shear force is going to be related to the friction coefficient times the amount it's being squeezed, right? But notice that shear force isn't going to really, it's not going to cause any dilation really, hardly at all, of the surrounding region, okay? And so I'm going to say that that's poor interlock. If I have a non-spherical shape, in this case, a clump of 3 pebbles, and if I rotate that thing, notice I'm going to build up compression here and tension here. It has nothing to do with friction. It has to do with shape. And notice also when I rotate that thing, that's going to, you can just see it's going to cause a big dilation. There's going to be a big local region of dilation. Okay, this is better interlock. Real granular materials are like this that are not spherical. They have all this interlock, which is essentially giving them additional strength, if you will, kind of. Think about doing a shear box test on this shape and a shear box test on that shape. This guy's going to have bigger internal angle of friction. It's going to have bigger shear resistance, bigger mobilized response because of that interlock. So this is the question. You want to get a PhD. Here's your question. Solve the problem. I want to make this system behave like this system. How do I do it? So someone came up with this. They have what they call a rolling resistance counting model. Here they do. Here's two guys. Here's a contact. There's going to be relative rotation difference between them. Okay. And this happens everywhere in a granular system. When you take a collection of spheres, as long as they're not all the same size, if they're all the same size, the spheres will pack into a perfect hexagonal alignment. But if you have a perturbed size distribution, a perturbed size and not all the same, they'll pack in this arbitrary way. And so that means when you squeeze it, what you will find is all kinds of rotations. They will all rotate a little bit. And so if there's a difference in relative rotation, what they're going to say is there's going to be a moment, a micro moment to resist that change of relative rotation. So this is how that micro moment is going to be related to the rotation. There's going to be a concept of a rolling resistance stiffness. So as I make relative rotation difference, so let's say this guy doesn't rotate and this guy is forced to spin. This guy, force it to spin. Don't let that guy spin. What's going to happen is there's going to be a moment resistance that builds up and then it reaches the limiting value. And that limiting value is going to be related to what they call the rolling resistance friction coefficient and the normal force. Okay. This system, when you do this model, it actually behaves amazingly similar and amazingly well. I'm going to show you a few slides that show this here. These are slides of work that's been done by Professor Corne Coetzee in South Africa. He's also actually been working with ITASCA for a number of years, and he's done a lot of work with PFC 3D. And he's done work with spherical particles, with rolling resistance, and then with clumps, with and without rolling resistance. Okay. And this is the one, oh, sorry, this is the paper we want to talk about. And here what he does is he compares these things. He compares spherical particles. So he compares these systems and these systems. And he uses this system with rolling resistance, right? Without and with, and then this system. And what he finds is that the rolling resistance systems and these systems behave very well. And so here's an example of the kind of stuff he does. On the left is corn, dry corn kernels. That's plexiglass glass in the front. And what he's got is an initial assembly, and then he removes a wall here and he watches the flow behavior as this stuff falls. On the right is his PFC 3D model with these clumps, right? Just show it again. It's pretty interesting. And so you can see the mobilized region here, right? And you can see the flow as it builds up on the bottom. So, okay, that looks okay, but what about the actual quantitative thing? And I'm just focusing on this. This is an email he sent me in 2020. He says, I was quite surprised that once calibrated, both particle types showed actually the same levels of rotation, which indicate that the balls with rolling friction not only provide the correct bulk response, right? So you can measure the bulk response, internal friction angle, right? But they also seem to give the right rotation actually inside. So there's something mechanistically reasonable about this rolling resistance thing. And so this is what most people do who are doing industrial scale mixing problems. They use spherical particles and they use rolling resistance. Okay. So just because I was curious, and actually I had some guy who was interested in modeling corn flow. There really was a guy in southern Minnesota who wanted to model corn flow. And so I did a little exploratory work to see. And so what I did is I said, let's reproduce that same system that we just saw. This system, let's reproduce this system with PFC 2D. And so I set this thing up and I put a bunch of particles under gravity. I made them colored. And then I'm going to open up the thing here. This is 107,000 particles. And so there we go. We let that thing go. It starts mixing. It all flows down, right? This took 10 hours on my laptop. I have like a 3-year-old laptop. Okay. So 107,000 particles. These types of problems take a long time because there's a lot of motion that has to get simulated. In a bonded system, you might just have a bigger thing and now you're just doing a compression test on it. That's relatively small amount of strain. But this is discs with rolling resistance. Seems to make sense. Let me just actually run this thing in PFC 2D. So I'm firing up PFC 2D. Lets me take a sip of my coffee. You know, we make it start slow on purpose so that you can take a sip of your coffee. Here's the full system. There's a cloud of discs. I'm looking at it from far away. This is a zoomed in view. They're not overlapping. We do that in one command. Now we're going to run this thing. We're going to watch them come to equilibrium here. They're going to form a pile and reach equilibrium, static equilibrium. We're going to see force chains build up as that happens. Watch what happens. And then we're going to open up a little hole here and watch them flow. It's all going to do it now. So this is modern PFC. Look at those force chains build up. Boom. Do you see that bounce back of the surface? And now we're doing this model solve ratio average command. We're just telling it, keep on going until you reach that criteria of 1e minus 5. See, there's not much going on anymore. There's still a little bit of bouncing its way at the top. You can kind of see that changing. We're almost there. There. Go. Boom. And now we're watching it run. So this is running. This is real time. Now, this is not the model with 107,000 particles. This only has maybe 2,000 or 3,000 particles. But, you know, there you go. PFC. It's running. Let me just show the beginning of this because it's such an interesting thing. Okay, shift escape. Come on, there we go. Run it again. Look at it this way this time. Watch the bouncing, how this thing bounces. Right? Very realistic. I mean, it really is behaving like a whole bunch of spheres. Okay. Here's this guy. That's what he looks like. And as we know, right, bigger, thicker forces on the bottom because of the weight of the stuff above, right? Here's the thing. I actually showed this a little before. This was a paper that people used PFC 3D to look at changing the shape of these ore passes and the alignment. This was the original ore pass design. Notice that as they were taking material out here, they emptied this one, but not this one. So then they went and slightly reconfigured the orientation, and then they were able to show they're getting flow out of both of them. This was a 3D model, actually. Here's the walls that represent the ore passes. This is just a cross section through the 3D system. I want to show this now. This is an industrial scale 3D discrete element simulation using particles that are spheres with rolling resistance. This is not done with PFC as far as I know. This is on a YouTube thing and it's extremely interesting and it kind of speaks for itself. Here we go. So watch this. This is a plate that's being dragged through the granular material. See that? The plate being dragged through there. And we're going to look and determine what the effect of the rake angle is, what the effect of. So here's what they notice when they do this in the lab. The force gets high and then low. It gets high and then low. Why is that? There's the DEM model. Can you see why it gets high and low? You can see here, right? Pushes, shear band forms, force gets low. Pushes. This is in many ways similar to that rock cutting thing that I was showing. And as that thing forms, it's changing the local volume fraction of the material, right? You can see, oh, look at this. This is so cool. It gets high, shear band forms, force gets low. This is the total force on the plate, right? Again, spherical particles with rolling resistance. And then here, of course, you're looking at the effect of rake angle, right? Which is must be affecting the force because it's affecting the orientation of these shear bands. I think this is amazing. This is so interesting. I wish they had written a paper. I don't know. They just have the title slide and they don't have a paper. I was at a conference and somebody pointed this thing out to me. So there we go. Here is some work by someone who was my IEP student
and he was a student at Berkeley with John Bray, who is a guy who does lots of soil mechanics work. And what they did is they looked at, could we model the proper behavior of soil mechanics? Like people know about soil mechanics. They talk about critical state soil mechanics, and there's all these complicated things that happen with soil, and a lot of them are functions of the initial porosity of the system. So what they did is they said, okay, we're not going to play games with rolling resistance. We want to get a soil, and we know that we don't want to use spheres. So what they did is they used these shapes. They were clumps, which means they don't change their shape. So that's this weird shape, right? You see this guy with the big one and two little ones, like two ears. They did these shapes because they wanted to just get angularity in the system. They didn't want to claim that they're modeling a real set of sand grain shapes. They just want to get angular grains. And then in addition, they matched the size distribution of a particular type of sand, Fontainebleau sandstone. Notice the thing I always talk about. This is the real sandstone size distribution. Notice the length scale, 10 to the minus 1 meters, diameter grains. What they did is shifted everything over. So their system has much bigger grains, and boom, they cut off the small ones. It's what everybody does. And so then they did shear box tests, and you can see different things here, the different behavior. This one is a function of the void ratio, that they created materials with different void ratios to begin with. And so these are the types of plots, like the vertical displacement. If the void ratio is high, it just does this. But if the void ratio is low, I can't remember, one of them's low, one of them's high, right? And it like expands or it doesn't expand. This business about, how it loads up. Again, it's a function of void ratio. These are all the sorts of things that you see in critical state soil mechanics. They basically say where the results are consistent with the principles of critical state soil mechanics. So this is giving us confidence that a PFC 3D model with some sort of non-spherical interlocking shapes, just with these clumps, is giving us the proper mechanical behavior. And that's what they found for these shear box tests. And then they're saying, well, then we can probably hopefully get the right behavior if we did other boundary value problems, right? So this is a paper that talks about that if you're interested in that work. This Garcia guy was the student. He's now a professor. I'm not sure where. The last thing I wanted to mention here is, again, spherical particles, rolling resistance. This was PFC 3D, 16,000 spheres. And they modeled this cone penetration test where you drive this sucker into this material, right? So, this is supposed to be soil. So ideally this should be infinite size, but they can't do that. So they made a chamber. Hopefully the boundaries are far enough away. They don't really affect the results. Okay, they calibrated this. Here's their calibration results for that material. And then here you're looking at it as you start pushing this in. And what they're showing here is this is that rolling resistance friction. And what they're showing in this one, I think, increases the zone of large force around the tip, which sort of makes sense, right? Because the more you crank this up, the more sort of an interlock effect, the more dilation you're going to get. So the more dilation you get, the more you mobilize a larger region. Compare this one to this one, right? These are force chain plots. Thickness is proportional to magnitude. And then here, again, what are they? Again, you're getting this effect as you increase that rolling resistance thing to where the action is happening, things like that. So again, they make a conclusion that this rolling resistance thing makes really good sense. Last thing I want to show is a super interesting deal. This is a failure that occurred in one of the largest open pit mines in the world. This is an open pit mine in Utah. If you fly in an airplane, remember we talked about flying at the 737 airplane level and looking down at the PFC contact models. Well, if you're flying over Utah, what you see is this enormous open pit. This is a 3-kilometer diameter open pit mine, okay? And
relatively recently, I think in the last 5 years, this whole entire section. Whoops. What the heck just happened? Oh, hang on. Hang on. Let me get that actual file. 'Cause they actually captured this on video of this failure. There it is. Let loose. Now then you say, oh my God, as a failure, how in the heck did they capture it on video? Well, because nowadays for these mines, they have little sensors all over and they're constantly monitoring motion of those sensors. And these sensors are so accurate, you could like look at motion on the millimeter scale. And so about a month before this occurred, they were detecting a rapid increase in the local surface motion in this region up here. So they were able to move everybody out of the way and get rid of their equipment. And they were basically able to put a camera on this for like a month. And the camera actually caught the entire failure. This is a kilometer like from here to there. It's an amazingly giant area. What they were wanted to know is there is valuable ore in some of this volume. And they wanted to know where the ore ended up in the final pile because that would guide their recovery efforts because they don't want to sort through everything. That would be too expensive. And they also had some monitoring. These are those little monitoring points they had. So they had some data for the ones that survived, like where they ended up. And they wanted to know where everything ended up. So they said, can you model this with PFC 3D? And we said, well, yeah, we give it a shot. And so what we did is took this real topography, made it with a big PFC wall. Okay. And this is the final failure surface. So we actually built the model with the failure surface in it. Okay. And then we flooded it with PFC spheres, PFC 3D spheres. And we carved off the ones that were outside of it. You can see the tops of the spheres sticking out of this region where we removed everybody. And then we assigned ore grades to all the different spheres and where they were in here. And then we basically just let it rip. And I want to show that somewhere here, there. And so there's the real slide. It starts on the right, and then it eventually works its way to mobilize this. And there's the PFC 3D thing. Again, these are spheres with rolling resistance. This had, oh, that's the facets. I don't know how many balls were in this model. Oh, there we go. 273,000 spheres were in this model. I don't know how long it took to run, probably overnight. And so that's all that I wanted to say as an example. That concludes the granular flow discussions that we're going to have in the course.